Hi, I'm AT. I work with Dr. Adrian Erichek at UNC Chapel Hill, and in my research, I investigate the very first second of the universe. What happened in this first second? There's lots of evidence to suggest that right after the Big Bang, there was a period of inflation during which the universe expanded very rapidly. Sometime in the first few seconds, and lasting into the first several minutes, elements other than hydrogen began to form in a process that we call Big Bang nucleosynthesis. It turns out that we don't know a lot about what happened in between these two periods in roughly the first second of the evolution of the universe. We know that the universe became dominated by radiation by the time of nucleosynthesis. And one group of theories for what happened in this first second is that the universe was first dominated by matter. And we'll call this period an early matter dominated era, or EMDE. In an EMDE, because the universe is dominated by matter, it's easier for dark matter particles to find each other and cluster into structures that we call halos. Here I'm showing you results from simulations done by previous members of our groups, and you can see that in a universe with an EMDE, structure begins to form almost 30 million years earlier than in a universe without an EMDE. And here I've highlighted the very faintest beginnings of structure we can see. Also, by the time that structure forms, there are more of these halos and they are smaller and denser in a universe with an EMDE than without. This is exciting news to us because I work with an annihilating model of dark matter, which means that when dark matter particles find each other, they can annihilate, creating a burst of energy, out of which pours a cascade of other electromagnetically interacting particles that can sort of talk to the rest of the universe. And these can serve as a sign that dark matter was once here and once annihilated here. If there was an EMDE early on, and if we have dark matter clustered more tightly into more of these microhalos, we can get something that we call a boost to the annihilation rate. Basically, we can get a higher dark matter annihilation rate for a given dark matter annihilation cross-section, which is a measure of how likely this process is to occur at all. If we have a higher annihilation rate, we have more of these annihilations, we have more of these injections of energetic particles into the intergalactic medium, or IGM, which is a bunch of dust and gas that floats out in space between and around the galaxies. These energetic particles interact with the IGM by ionizing, exciting, and heating it. And all of these processes propagate to something we can observe today, the cosmic microwave background, or CMB. The CMB is composed of radiation that comes to us from the moment when the universe became transparent 380,000 years after the Big Bang. The data that we have on the CMB comes to us from the Planck satellite, and here I'm showing you a temperature map of the CMB, where all of these red and blue patches are small fluctuations away from an average temperature of roughly 3 Kelvin. One of the things we can do with this temperature map of the CMB is to create a temperature anisotropy spectrum. We construct this by choosing an angular scale, say this one, measuring the CMB at 2 points separated by that scale, then measuring all of the pairs of points that are separated by that same scale, and getting the average temperature fluctuation for this separation. Then we repeat this for lots of other angular separations, and we get a spectrum that looks like this for the average temperature fluctuation as a function of the angular separation of the points. Here I'm showing you an example of my results for the temperature spectrum of the CMB, calculated both for what we actually see in the CMB today in gray, and then 3 EMDE scenarios. And the annihilation parameter that you see in the legend here looks like this. It is directly proportional to the dark matter annihilation cross-section and inversely proportional to the mass. Basically, it's a descriptor of what dark matter model we're working with. And so when we look at this figure, what we see is that for a particular EMDE scenario, I can bring this annihilation parameter down almost 10 orders of magnitude and still get a CMB temperature spectrum that looks almost identical to what we actually see in the CMB today. Being able to broaden the range of possible annihilation parameters this much also means broadening the range of viable dark matter candidates. And so this is a great example of what the CMB can tell us about what kinds of EMDE scenarios were possible early on in the universe, and also what kind of dark matter could possibly exist today. In the rest of my project, I'll be looking at different values of the cross-section and dark matter mass, for different values of this annihilation parameter, and also looking at other cosmological parameters like the optical depth to see what else the CMB has to tell us. Thanks for listening, and thanks to NC Space Grant for supporting this project.